All right, so let's look at experiment number 6. So as you know, we are using circuit simulation as a tool to understand and design circuits. And in this particular experiment, lab number 6, we'll continue with the diode circuits. In the last experiment, we have seen design of power supply with and without a Zener diode. In this particular lab, we'll explore several interesting circuits. All right, so let me open up the simulator and let's start the discussion here. All right, so the first two circuits are what we call as clamper circuits. So what you see here is, for example, a sinusoidal source. So let's say this is 4-volt amplitude and 100 hertz frequency. And suppose we have this particular arrangement where we have a capacitor and a resistor and a diode here. And we are using a relatively fast diode here. Fast in the sense, if you double click on it and you look at the model, and you go down here, one of the elements of the speed of a diode is what we call as the transit time. And so transit time is about, let's say 9 nanoseconds. So it's basically an indication that the diode can switch in, basically time periods equivalent to about let's say 1 or 2 times the this transit time here. So if you typically switch off a diode, it will switch off in maybe not exactly 8.9 nanoseconds, but maybe 10-20 nanoseconds. All right, so it's a pretty fast diode, and especially compared to the frequencies that we are using, 100 hertz here. But you could use 1 kilohertz, 10 kilohertz. The circuits, the diode will behave fine. All right, so the reason why we are saying is that we know that diode conducts in the forward bias direction and does not conduct in the reverse bias. But, when you switch a diode, for a brief period, it conducts in the reverse bias. For a brief period, because there are charge stored and diodes have capacitances, so those capacitances have to discharge. And so for a brief period, it conducts, and that period is what is related to that parameter called transit time. Right, so all these circuits, that we are building using diodes, they rely on the fact that in the reverse bias, the diode doesn't conduct, and in the forward bias, it allows the current to pass. Anyway, so that's about a diode. So this particular circuit, clamper circuits, is something that you've studied during the theory part, and that's something that you can explore using simulation. And so basically what happens is, so let me simulate. So 100 hertz here, capacitor is there. We would like you to explore the impact of R1, choose different values of R1 and see how the circuit works here. So if I do a transient simulation, and we are running it up to 100 millisecond, and let's look at the output here. All right, so the output is, the blue one is the input here, and the red one is the output of the circuit here. And the circuit, what it is doing is taking the input and pushing it up such that there is ideally the whole waveform is positive. The whole waveform is above the 0 line here, and so it's a positive clamper. Whatever is the negative portion here, it will push it up so that the entire waveform is shifted up, and there's very little negative part here. Now we do see that there is a little bit of a negative part here because the circuit is because of the diode drop. There's a drop across the diode, and that's the reason, if you analyze, that you get this little bit of a portion here. And so what you can do is, as we said, so you can explore the impact of a resistor here. You can see why, you can try and understand the operation of this particular circuit by looking at what happens in the positive cycle here. For example, you see here that as you switch on, it goes here and follows here, and then this particular part here, and then it shifts up. So how does this actually happen here? So during the positive part here, of course, the diode is off, and this part of the circuit is acting here. And the time constant chosen is such that the capacitor is not able to charge here. So basically not able to charge. But in the reverse case here, the moment it goes negative, so the capacitor is like transparent, right? So the voltage across the capacitor, you can monitor the voltage across the capacitor. The fact that you see here that the output follows the input here, right? Follows the input here during the initial part here. Output is following the input here, which means the drop across the capacitor is negligible. It's not able to charge here. So that's where the role of the time constants and all that you will explore. In the reverse bias, what happens is the moment you go reverse bias, well, the diode offers a low resistance path and the capacitor is able to charge in the negative direction here. It's able to charge in the negative direction except for the diode drop here. So the capacitor acquires a charge here or a voltage here. Then when you go in the positive direction here, this particular voltage along with the voltage across the capacitor, they add up, resulting in a net value here. All right, so I mean, that's the basic way in which this particular circuit works here. And you can explore that using simulation, okay? Especially by looking at what happens to the capacitor, the voltage across the capacitor, and not showing it. So you can plot also this node voltage minus this node voltage will give you the voltage across the capacitor. And you can look at it, how is it charging, how is it discharging, and explore that. So that's a clamper, positive clamper. And if we reverse the polarity of the diode, we get a negative clamper here, right? So what it will do is ensure that the whole waveform is shifted downwards so that there is no, the entire waveform is negative. There is no positive part of the waveform here. All right, so that's a negative clamper, and then there is a positive clamper. So each one of those circuits you can study. Then there is another circuit which we call as peak follower, right? So what this particular circuit, as you can see here, what will happen is as long as the input voltage is larger than the voltage which is there on the capacitor, the diode will turn on and will charge up the capacitor. But if the voltage here is less than this, then the diode will be reverse biased and the capacitor will retain its value. So anytime the voltage exceeds the capacitor voltage, then the capacitor will charge up to that particular point here. Of course, there's a diode drop that is there here. And so the output voltage will then follow the peak value here. So to study that, what we have done is, if you can go and select a voltage source from here. And so let me double click the voltage source. And to get an interesting waveform, not simply a sinusoid or a triangular wave, what we have used is a noise. A noise is like a random, input here. So we've chosen the noise part here. And noise, it will generate at intervals of 1 millisecond. We'll take an amplitude of 10 and end time is 100 milliseconds. So it will generate a waveform for a total period of 100 milliseconds with some random variation that is there here, right? And let's see how the circuit works here. So note that the outputs are V peak and V peak here. So let's do the transient simulation. So let's disable these ones here. And let's look at this part here, okay? So the first one is the input and the next one is the output here. So let's run it. Right, so note that this is the output here, random, signal that is there here. And this is the output here, output of the peak detector. So it charges up here and then it tries to note that there is a diode drop that is there here. So it tries to follow this particular peak, then it follows this particular peak. We can run it. Every time you run, there would be a different random voltage here. You can see how it's trying to follow the peak here. Now it's not a perfect peak follower circuit because of the diode drop. Let's run it once more. Yeah, here you can see nicely here. This tries to follow this. Then the voltage exceeds, the input voltage exceeds the capacitor voltage, so follows here. Then it follows here. So it tries to follow the peak part here. And it's not able to follow this peak because, it's not more than the value of the capacitor voltage by a diode drop, so it's unable to follow here, these ones here. So there's an error because of the diode drop. Otherwise, it tends to follow the peak value here. Right, you can run it once more. every time you run, you'll get a different random voltage here, and you can see how the peak detector circuit works here. All right, so that's the peak detector part. The next one is we're going to use the clamper and peak followers to create interesting circuits called doublers and triplers. So this particular circuit is a doubler circuit. So what it does is you will recognize this particular part here, this part here. This part here is nothing but positive clamper. So whatever is the waveform here, let's say is a 10 volt sinusoid. So what it will do is it will shift it up and such that there is no negative part there, right? So the peak value then will become 20 and minimum value ideally will become 0, right? So it's 20. And this part is what we just saw is a peak detector circuit, right? So it will capture the peak value, which is 20 volt, right? So from basically 10 volts sin omega t, we are able to generate a value equal to 20 volts here. So let's see this working. So let's do the transient simulation here. So I already entered all the values there. So this is there and this. Right, so let's run it here. Okay, so you can see the doubler circuit working, and the value of the voltage is, all right, the value of the voltage is 18 volt. It's able to generate. Note that steady state value is about 18 volts here. Ideally, we would have liked 20 volts here, but because of the diode drops, there is error there because of the drops in the diodes, and we are able to get only 18 volt. 10 volt is the sinusoidal amplitude, and we are able to get 18, so close to double, with some errors because of the diode drop. All right, so that's something that you can look at how the capacitor is charging, how is the peak value being captured by this particular part of the circuit. Now, once you make a doubler, you can make a tripler. So in this particular circuit, this is the part which is the doubler part, which we just studied here, right? And now what we did was, if you look at the doubler circuit here, the doublers, this one is ground, right? And so what we have done is we've connected all of them up, and instead of ground, we have raised it up by the amplitude here, 10 volt here, right? So the whole thing gets shifted by another 10 volts. So we had 18, ideally we would, this particular circuit will give you 20, but then if you combine these three nodes here and raise the reference level by 10 volt, then it will become 30 volt. So that's something that is being done here. So this is the doubler part here. And how are we generating the value here? So this part, note that what will happen is that during the positive cycle here, except for the diode drop, this capacitor will charge up to around 10 volt or so, right? And so this provides the reference of 10 volt, and then the rest of the circuit works according to the way we just saw. So we can simulate and see whether it triples or not. All right, so let's disable the doubler part there and enable the tripler part here, right? So let's run it. Okay, so let's see what is the amplitude here. So we get 27 volt here. So instead of 30 that we expect, again, because of all the diode drops, there are several diodes that are there in the circuit, and each one has a drop of 0.7, 0.8 volt here. Note that if we take 0.7 volt drop here, we expect at least 3 diode drops, so you can see the errors that are likely to be there in volts range here, right? So it's giving you close to the value that we want here, roughly triple the value of the input sinusoidal amplitude here. All right, so that is there here. You can explore the effects of, I've not given here the effect of this particular capacitor. As you make it small or large, what really happens at the output, and you can figure out what is the constraint on this particular value here, right? So that's a tripler circuit. Now what you can do is also think about how you can make you can quadruple the amplitude which means by a factor of 4 or 5. You can explore all of those other things also. You can construct those circuits, simulate it, and validate your design. All right, so let's close this here. And the reason why doublers and triplers are important, as an example of an application where they're important, is if you look at RFIDs. So you have a RFID tag which is there, and you have a reader. And so the reader sends in a electromagnetic signal, an RF signal, to the tag here. And in simple tags, the tags are passive in nature. They don't have a battery. So what they do is the RF signal which is sent here, you can see a coil, an antenna. So it generates a sinusoidal signal here. It's a tuned resonance circuit, and it absorbs the power, and the RF signal, a sinusoidal signal, is generated. Now this shows a tag in more detail here. So there is a basically an LC tag circuit here, which the goal is to generate the RF signal. And there is an IC here. So there are circuits here. So the entire circuits are powered by the signal which is captured by the antenna here. So when you capture the signal here, the voltage, sinusoidal voltage which is generated, is often not of sufficient amplitude. So we would like to, for example, let's say the amplitude is 1 volt, and my IC requires 3 volts to work here. So then that 1 volt has to be tripled. So we need a tripler circuit to increase the amplitude to 3 volt, and those 3 volt can then power the IC here. And once the IC operates, then it can generate a signal which is sent back to the reader. The identification information can be sent back to the reader that is there here. So these doublers and tripler circuits are one places where they find application is in circuits, in RFID readers, basically in RFID tags. They can be useful there. And of course, there are many other places wherever, let's say, your input amplitude is not enough for the circuits, then you would like to boost it up. And one way of doing that is through circuits like these here. All right, so let's stop here.